All right, I hope everybody had a good spring or Thanksgiving break. We got 3 weeks here. 3 weeks, hopefully. Again, the goal is in this 3 weeks we will finish up what we need to finish up, and we have one chapter left to go here. With that one chapter, we'll have chapter tests, and then the last week we'll have a final for this section of college algebra. So you'll have a final before we go on break, which I think is better for you. Also, with respect to for Downton High School, we have to give a final for Downton High School for every one of the classes. What I will do is the final we have here will be like a midterm. I will combine this final that you have here with the final we have to have with trigonometry, which is the second half of the year. And we'll combine that for the Downton High School final then. So we won't have to take a third final. Okay, so we'll just take 2 college finals here before Christmas break, and one in probably about the end of April, is when we get done with everything trigonometry. And then I'll fill in May with other things. But I will combine both of those together to give you a pre-calc final for Downton High School. But we have one chapter left to go. The one chapter we have left to go deals with exponential functions. The idea of an exponential function is any function that has a variable as an exponent is an exponential function. We will deal with logarithms here in this section, in this chapter also, which are things that you should have been able to do or should have done when you're back in the algebra, in algebra 2. But when we talk about an exponential function. When you talk about an exponential function, once again, you have a variable as an exponent. And this will give us an exponential function. Well, we have a value in the mathematical world, which is a value of e. Okay, this value of e is called Euler's number. Now, we're American, we're hooked on phonics. We want to say, well, this is Euler's number because EU will give us Euler. But if you're over in German or in Europe, that would be an Euler idea. So this is O-I-L-E-R, pronounced Euler's number. It is a constant just like you have for the value of pi. When you have the value of pi, we approximate 3.14, but we can go on 157, 18, 28, and so on throughout. That is our value of pi, approximately, but it will continue on indefinitely without repeat or a pattern. So this is an irrational number. Because it never repeats and never terminates. Euler's number is the same way. Euler's number is approximately equal to 2.718. What's important about Euler's number is it will go into your exponential growth, decay functions that you'll be dealing with in chemistry. It will take you into an exponential growth function or decay function in any type of investments that you deal with. So you can use Euler's number, and is used in regards to exponential growth, decay, and anything that you're dealing with, whether it's money, whether it's chemicals, whether it's half-lives of atoms, whatever you have. That's your Euler's number. Well, if we take a look at Euler's number, your calculator also has a new function. If you look at your calculator, along the left-hand side, you have an ln button on the left-hand side. You have an ln button here. What you also have is you have an e to the x button. Now, if we remember correctly what happens with our calculator, how our calculator is set up, a lot of times is you'll have some sort of mathematical function to deal with here, but the second function is the undoing or the inverse of that function. Where if I square, I can take the square root. It undoes what you did. If I take sine, cosine, tangent, I can take the inverse sine, cosine, tangent. Undoes what you did. Well, your ln, which is a logarithmic function, can be undone with an e function here. Your log button can be undone with the 10 to the x power. So these are all exponential ideas. When you look at, you have e to the x, you have your e to the x, that's your exponential function, or you can have 10 to the x, or anything to the x power, which will undo, excuse me, a lot of your exponential functions. And that's what we'll be discovering and looking through in this last chapter is your exponential function idea. So what we want to do is we want to graph our e function. We want to graph our e function. And how we can do this is by putting in values and solving for y. We can just do ordered pairs. We have our x and we have our y. I'm going to go out 2 spaces here. Going upwards, we can go up 1. And what I want you to calculate is, you can go e to the negative 1, e to the 0, e to the 1, e to the second power. We'll go 4 values here. I want you to calculate these values. And you can use your e function on your calculator, or if you want to, you can go into your y1. You go into your y1 and type in e to the x power and do your values and find your values that way. And what that will also give you is that will also give you a graph. So you can do it either way. Or I could just go, let me curl that out. Second e, it gives me my e function and go -1. And find my value, or if I want to, I can go in my y1 and go, this goes second e to the x, and do my value. This will also give me my e function graph. Now I can type in -1 and then 0. Either way you can come up with your values, that is fine. Or if you want to do your table, I can start at -1. We can increment this out by 1s. And I can go to my table and find my values that way. And I can get my graph down. At x equals -1, I got 0.37. Then we have 1, 2.718. And at 2, we have 7.38. And if you take a look at our picture of our graph, what we will come up with our picture of our graph it is not going to be a linear function, it will be an exponential function. This would be an exponential growth function. Why we call it growth is because as x gets bigger, y will get bigger. That's an exponential growth. We can also have an exponential decay function. Which will be as x gets bigger, y will get smaller. That's your half-life functions. When you look at your chemistry and your chemicals, you talk about half-lives. When we talk about half-lives, that is a decay function. And what will happen is, with an exponential decay function, you will start in the second quadrant and then flatten out here. That would be your exponential decay function. Well, what we have here is we have a graph, exponential graph function that's going to be asymptotic. At the value y equals 0. Okay, we talked about asymptotes in our previous section when we were graphing rational expressions. Okay, we will flatten out along the x-axis or the y equals 0 function. Well, we can start taking a look at translations. And we worked with horizontal and vertical translations in previous sections. If we take a look at our same values here, we have y equals -3 plus e to the x. So if you want to type into your y2, -3 plus e to the x. And take a look at what happens with our graph. Judah, what happens to our graph? Yeah, we have a vertical translation of -3. So every one of our points that we just put up here, we can count down 3 positions. 1, 2, 3. 1, 2, 3. 1, 2, 3. And 1, 2, 3. Our asymptote now is going to be y equals -3. So at -3, we're going to have this asymptote here. And our graph's going to look the same, but everything just gets shifted down 3. If we look at e to the x minus 4 graph, so if you want to in your y2 again, type in, make sure you keep it as an exponent or a quantity, x minus 4. Everything gets shoved to the right 4 positions. So if I go back to my original graph, all these points get shoved to the right. Four positions. We still have the asymptote at the y-axis, y equals 0, but everything gets shoved to the right 4 positions. If we have e to the negative x, what happens to our e to the negative x? And basically all we're doing is going back and going through the idea of translations, what our translations are, and our reflections. Make sure you use the negative sign at the bottom, not minus x. What do we have with this one? Goes the other way. So what do we have in regards to a reflection? So we are reflecting. About the y-axis. So this point comes over here. This point stays the same. This point comes over here. And this point comes over here. So we have a reflection about the y-axis. So we have a vertical translation here. We have a horizontal translation here. Once again, we have vertical translation plus any e to the x minus our horizontal translation. So we should have a vertical translation of 4 here and a horizontal translation of -3. So if you would type this into your y2 now, you should see a slide of the graph vertically, horizontally. It's just going back and reviewing our ideas of verticals and horizontal translations, but putting it into our e function now, or any type of exponential function. And if we go to the back and we look at any c to the x power, it doesn't matter what the c value is. We use e, but it could be the value of 2, it could be the value of 3, it could be the value of 5. It doesn't matter. Whenever you have our variable as the exponent, that will give us our exponential function. So it doesn't matter if you deal with e, or the value 2, or the value 3. If you would just graph y equals, in your y2, y equals 3 to the x. And compare that to y equals e to the x. Your graph should look very similar to y equals e to the x, because 2.718 is very close to 3. So it should be very similar to it. Any exponential function is going to look very similar to what we just did, whether it's e to the x, or 3 to the x, or 5 to the x. It's a matter of whether it gets a little bit quicker, or bigger, faster. So I'm not going to go through this. I'm going to come down here to the bottom here and solve some exponential equations. If I ask you 5 to the x is equal to 25, and I want you to solve for x, I would hope that with your math knowledge that you have up till now, you'll be able to figure out what value of x do I need to put in, so that when I take 5 to that power, I get 25, which would be what? 2. Yes, it should be a value of 2. But when we start getting a little bit more involved, 5 to the x equals 1 over 125, or 5 to the x is equal to 625, or 5 to the x minus 6 is equals 125 to the x. Now it becomes a little bit more complicated. If a equals b, and then a to the x is equal to b to the x. Let me go change that. B to the y. Then x must equal y. If you have a like basis, and you have them to exponents, and you have equality, then the exponents must be equal. So if I take a look at 5 to the x, we'll go back to the very simple one here. 5 to the x is equal to 25. I want to be able to write 25 as a base of 5, which would be 5 to the what power, Olivia? 2. 5 to the x equals 5 squared. If a is equal to b, if my bases are equal, then x must equal the value of 2. Our exponents must be equal. Well, if I take a look at 125 we can write as a base of 5 to what power? Third power. Well, we get to review our idea of exponents here. Some ideas of exponents. I want to be able to get these to be a to the x is equal to b to the x. Well, I have a to the x is equal to 1 over b to the x. I want to get them both in my numerators are both on the same level. One's a reciprocal, one's a denominator, one's a numerator. How can we take 5 to the third power and write it as 1 over 5 to the third power? How can I rewrite this as 5 to some power? Do we remember? What exponent can we take 5 to equal 1 over 5 cubed? Well, if we review some of our ideas, if we have a like basis, we can add our exponents. If we have division here, we can subtract our exponents. If we have 1 over x to the a power, we can rewrite this as x to the negative a power. So a negative exponent, what it does, it switches us from numerator to denominator, or denominator to numerator. So if I have 1 over 5 to the third power, we could write this as 5 to the negative third power. To take it from numerator to denominator, denominator to numerator, we can just switch it from positive to negative or negative to positive. So what we're left with is x is equal to negative 3. So in your calculator, if you would type in 5 to the negative third power, hit your math button, hit enter, it should take you back to 1 over 125. Your goal is to, as you rewrite this, you want to be able to rewrite this as a like basis. So I have 5dx minus 3 is equal to 625. Well, I want to write that as a base of 5. We want to get our bases to be the same. So 625 can be written as 5 to what power? Fourth power. So now if I have a like basis, the exponents must be equal. So x minus 3 must equal the value of 4. So x equals 7. Or 125. Once again, 125 is 5 to what power? Third power. So we have 5 to the third power to the x power. Well, when we have a power to a power, when we have a power to a power, what do we do with our exponents? Multiply them. This is x to the a times b. So if I have 5 to the x minus 6 equals 5 to the 3 to the x power, I have a power to a power. We multiply our powers, our exponents. So we have 5 to the x minus 6 equals 5 to the 3x. We have a like basis. If we have a like basis, the exponents must be equal. So x minus 6 equals 3x. We subtract our 6 over, or our x over, and then divide by 2. (81 to the x plus 2 or 9 to the x plus 2 equals 81 to the x. Now we can do this one of two ways. We can write 81 as a common base of 9, or we can go 3 to the x, 3 squared to the x plus 2 equals 3 to the 4th to the x. Powers to a power. We're going to have 2 to the x plus 2. And then our exponents must be equal. We could also write this as a base of 9. Either one will get you the same answer. Very quickly. How do we write square root as an exponent? So we have 3x equals 1/2. We can divide or multiply by 1/3. Once again, another property of exponents. X to the AB power is the bth root of x to the a. Once again, these are all properties that you had back in algebra, that you worked with back in algebra. And this allows us to take a radical or a fractional exponent and move it into a radical. Again, we're tapping into everything that you learned exponent-wise back in algebra. Again, it's important that we keep up with our material here, because we will continue to push through. In the first one, what I want you to do is first just graph y equals 2 to the x power. So get points down there, get 3 points, 4 points. Okay, I say 3 points, you get 3 points down, 4 points, does not matter. And then for each one of them, what is your vertical translation or horizontal translation? And rather than plugging in values into the function here, just work your vertical horizontal translations. Take your graph that you have, take your initial graph, and just move the points. Down one, to the right one, left one, up one. Whatever your translation is, just move the points. Move the points. Alright, solutions are posted. Have a good day.
Yeah,